Right. Let's talk about Monty Hall's problem. We have two. So first, let's talk about notation. First, C stands for car, S stands for sheep. So we have two sheep, one car, and you choose each. There are three doors. You choose one of them, and after you choose one of them, the host reveal one of the door that is sheep, and the host will ask you, do you want to switch? So let's calculate the probability of the chance of winning if we switch or not. At the beginning, I thought it's easy, half and half. If host eliminate one sheep, then you got one car, one sheep, right? Just no brainer. But I ended up finding that I was wrong, which is sad. But let's use because my calculation is using the assumption of host. Choose randomly. So the probability of winning if we not switch is basically the probability of U, Y stand for U, H stand for host. You got a car under the condition of host getting a sheep. So from condition probability, you know that it's the probability of both happening divided by the host choose a sheep, which is 1/3 divided by 2/3. It's 1/2. Then of course it has to add up to 1. Probability of switching and unswitching, then it's half and half, easy. Also another really easy way of thinking about it, of course this is a wrong this way of thinking is wrong. Just keep that in mind. It's another easy way to think about it, just like we have car, sheep, car, sheep, car. I mean, and then see you choose the first one. That's what you choose. And the host gotta choose a sheep. Then your probability will become, CSS, and the host choose a sheep. There's one car, one sheep on the door, so if you switch or not, it doesn't make much difference. It's half and half. But this is actually wrong. So the reason why it's wrong is that the probability of host choosing a sheep is 1, because it's always choose a sheep. That's the rule of the game. So the probability of not changing, end up become 1/3. So if we look at the more detailed picture, if you actually don't believe me, and also I actually still have self-doubt about this, but on the first class of probability, we've always been told there's always a no matter how hard the problem is, there's always a foolproof way to solve this problem. It's just least all the possible scenario, which is what I'm going to do now. So obviously we have a door A, B, and C. We have car in the door A, car in the door B, car in the door C, car in the door C. And there's 3 ways of you choosing. So I have to erase this. Remember, C stands for car, S stands for sheep. And Y stands for you, so you can choose. You can choose number first one, choose the second one, choose the third one. Same deal here. And so the host have to choose one sheep. So it doesn't matter which order he choose. So which other sheep the host choose. So we can just choose this one, or that one, sheep, right? So this one, or that one. This one. So that means that that's what host choose. So if we define winning as 1, then let's see the switch and non-switch. Or just stay. So it's on A. Here. So as you can see, if you switch here, you won't get the car. If you stay, you get car. If you switch, you got car. If you stay, you don't get car. Same deal here. And same analogy, switch, get the car. Now switch, no, sorry, this is switch got the car, stay got the car, switch got the car, stay don't got the car, oh, sorry, switch get the car, switch get the car, stay doesn't get the car. As you can see, for each scenario, if you switch, you have 2 ways of getting the car. And please correct me if I'm wrong. I'd be really happy if I know this and if this method is wrong. But I think it's foolproof. I think all 3 events have the same probability distribution. Because the host will intentionally choose the sheep instead of the random choose. So it doesn't have a 2/3 and 1/3 probability distribution of choosing a car or a sheep, because the host won't reveal the car. Reveal the car. That's how we get the 2/3 probability of winning on switching. And please tell me if this method is right or wrong. If it's wrong, please tell me why it is wrong. Thank you.